Here we're going to be looking at question 38 of the ENGAA 2018 paper. In this question, we're given the following scenario. We have a block on an angled slope at an angle theta, a distance L along the slope from the ground. We're told that our block has a mass m and that there's a frictional force acting against the block sliding, given by F equals K W sine theta, where W is the weight of the block. The question then asks us, what fraction of the initial potential energy becomes kinetic energy when the block reaches the bottom of the slope? Now it's also worth noting that the question tells us that zero potential is at the ground, just so that we know where our potential energy is measured relative to. If you'd like to have a go at this question, pause now, otherwise let's go ahead and have a go. Since this question asks us what fraction of the initial potential energy becomes kinetic energy, probably the first thing we should do is try and find this initial potential energy. So what is the potential energy of our mass initially going to be? Well, it's just going to be the gravitational potential energy. And how do we try and find this gravitational potential energy? Well, we would just use the equation that potential energy, which I've called E here, is given by the mass of our object multiplied by the acceleration due to gravity multiplied by the height of our object, which I've called h here and labelled in our diagram. Now the next thing to do is try and find out what h is going to be in terms of some of the variables we were given. What we can do is have a look at our diagram and realise that we've got a triangle here made up of a length L, an angle theta, and this height h. So we can try and resolve this, use some trigonometry, to find out what h is going to be in terms of L and theta. Doing this, we find that h is equal to L sine theta, so our equation for the potential energy becomes this. So the next thing we want to do is try and find the kinetic energy of our mass at the bottom of the slope. But how are we going to do this? Because we have a frictional force acting, so we can't just equate this to our kinetic energy. Instead, we have to work out how much of our energy is transferred or wasted, due to friction, and then the remainder is going to be converted into kinetic energy due to conservation of energy. So if we go ahead and find out how much of our energy is converted into heat by our friction, then we could use this to try and find out our kinetic energy. So actually the next step is going to be to find the work done by our frictional force. So how is it that we find work done by a force? Well, the work done by a force is just equal to the magnitude of the force multiplied by the distance the force acts along, which in this case is just going to be L, the distance along our slope. If we go ahead and substitute in our expression for F, then we find that the work done due to friction is this constant K multiplied by the weight of our mass, sine theta, and then multiplied by L, the distance across the slope. Now we know that the weight of our mass is just going to be the mass m multiplied by the acceleration due to gravity g. So by substituting that in and rearranging our letters a bit, sticking our L in here, we see that the work done due to friction is just this expression here. So it's actually just this value K multiplied by our initial potential energy. Now, moving on, we can go ahead and use our potential energy and the work done due to friction to try and find the kinetic energy of our mass at the bottom of the slope. So what's this going to be? Well, the kinetic energy is just going to be our potential energy minus the work done due to friction. It's just going to be this expression here, mgl sine theta, take away this expression here, k mgl sine theta. So if we bear that in mind, then we can go ahead and try and find what the question is asking us, the ratio of the kinetic energy over the initial potential energy. So our kinetic energy is just our mgl sine theta, take away our k mgl sine theta, all divided by our initial energy mgl sine theta. Now, as you can tell here, mgl sine theta is going to cancel out with in the denominator with the term in both terms of the numerator. So all of this is going to simplify down to just 1 minus k, which is quite nice and matches up with answer B.